It's a pleasure to be invited to this conference and give a keynote speech about my favorite topic, interfaces in batteries. I'm Kristina Edström. I'm a professor of inorganic chemistry at Uppsala University in Sweden, and I'm going to share my screen. Interfaces and interphases in batteries refer to, in particular, the negative electrode when it comes to the interfaces with pH, and for interfaces in general, the positive electrode and between particles and to current collectors in batteries, etc. We call it interfaces, which is sort of the normal word. I'm not only the leader of the Edstrom Advanced Battery Center, which is to be in Sweden, a quite large group of scientists. We are about 90 people in our group working in Uppsala, but I'm also the coordinator of a large-scale research initiative called Battery 2030 Plus in Europe, and we are in particularly studying the interfaces in batteries. We started sharp 1st September last year. We have 80 countries on board and 102 partners in different sort of sub-projects in this umbrella where I am the coordinator. I'm also coordinator of a much smaller, but still a competence center to Swedish academia and industry in Sweden, and part of excellence center in Europe called Ionically, which existed for quite a number of years now with some of the best scientists in Europe. And I will in particular focus on these interfaces with the pH and S. And this solid electrolyte interface is primarily formed on the negative electrodes in lithium batteries, in sodium batteries. And interfaces are formed in every battery, of course, but in this case, it's a bit thicker, it's a bit more complex. It's a mixture of different compounds. And it's actually a necessity specifically for lithium-ion batteries where we have graphite as a negative electrode. And it's really the prerequisite why graphite electrodes work for lithium-ion batteries. At the start, when people started to try to use graphite at the beginning of the 1990s, it actually, the organic molecules, solvent molecules, and the salt you had co-intercalated and started to gassing the batteries and exfoliating the graphite. And then the right kind of electrolyte solvent components were found, and this could form this solid electrolyte interface, which grows to a thickness where the electron cannot tunnel through it. And by not being able to tunnel through, it's not continuing to degrading the electrolyte, so this reaction stops that degradation. We are at potential very close to that of lithium. Lithium is the one which is at the far end of the electrochemical series, so it's very difficult to stabilize it. But on graphite, you can do it with this SEI, as we call it. But this SEI also converts and stabilizes where the lithium is intercalating and deintercalating through this layer, because it has to allow lithium transport. And you also have some dissolution. You can have lithium plating. I saw there's another presentation on that at this conference, which is an extremely important thing, and subsequent corrosion. I will show a lot of results using photoelectron spectroscopy, and a lot of the knowledge we have today is actually based on this technique, because if you look at the thicknesses of these SEI layers, they are in range of 30 to 100 angstroms. There are very few other techniques where you have this surface sensitivity to really depth profile and say something about the composition of the SEI. If you go to the positive electrode, which is far from this reactive lithium potential, like even 4, maybe even higher, you actually don't have this kind of SEI. You have instead what we call today a cathode electrolyte interface, which is more like corrosion products, HF formed, reacting here. So both the surface of the electrode as such can rearrange, but you have much thinner and a little bit different composition of this. There are several models trying to explain what you have in this SCI. On the negative electrode, here is one early from pellet. It's a mosaic type of structure. It's very often shown today too. It's I think in its composition very hampered of the time where we were not able to control the amount of water in the same way as we are doing it today when we are working in a protected atmosphere to make our batteries and dry our electrodes, etc., and our electrolytes. But it's he showed at least the most important things. A little bit later, Professor Auerbach, also from Israel, like Emmanuel Pellet, showed it more to be a inner layer where you have the SCI components consisting of what we could say more of inorganic species, and then of course some organics as well, and then you have like a mushy organic layer on top. We in our group, I'm very proud to be mentioned at the same level as these two pioneers by Professor Mantiram in his paper, showed it to be a little bit of a mixture of these two, where you have inorganic layer in close to the graphite surface, also with some organic compounds. But depending on how you treat your electrode, you get crystals or lithium fluoride, and these crystals can be of very varying size, dependent on how you have treated your electrode, what anion you have in your lithium salt, etc. So over-exaggerating also the heterogeneous type of layer you have on the surface. It's actually here in this model as well that it's heterogeneous. And in practice, the SCI is composed of inorganic compounds, lithium fluoride, very important, lithium oxide, less of that, some salt reduction products, and organic components like alkyl carbonates, PU type species, polymer types, a whole range of suggested compounds. So I will focus on photoelectron spectroscopy, but there are many other also kinds of methods you can use. I would say that in particularly NMR is now coming as a very interesting complement. But of course, you can learn a lot about these interfaces just by looking at the electrochemical signals as such, and you need always to complement it with SEM and TM studies. So all these methods, more or less, and the results so far that we have are based on post-mortem studies. You make your battery, you cycle it, you open it, and you take apart the parts, and you maybe wash and so on, and use this electrode. And what we really want to move to, it's operando. It's coming now. It's coming from many solid interfaces, the gas solid interfaces, but the liquid solid ones, they are tricky. I will show a little bit at the end about that. We also need to have a resolution to really probe the liquid solid interface formation. And how to handle that is also a bit tricky when you're using photoelectron spectroscopy techniques, and I will mention that briefly. And of course, we need to probe a number of different phenomena like aging, fast charging effects, roller temperature, safety issues, etc. So there's a lot of work and a big matrix to learn from. We started to use photoelectron spectroscopy techniques early, both in-house and the old Max lab in Sweden. And this is a simple study where we actually showed how just the influence of the salt, where we compared LiPF6 and LiBF4. And at that time, at the end of the 1990s, it was not really clear. We worked with a battery producing company in Denmark that existed at that time, and it was not clear whether they should use the more in the laboratory stable in the bottle, LiBF4, or the more unstable, LiPF6, a little bit more expensive. LiBF4 was better with the cathode, but it was something weird with the anode. And we could show by making some kind of simple storage and cycling experiments, pre-cycling an electron 3 times, storing it for 1 week at a certain temperature, then starting to cycle it again. And in each case, we needed to reform the SEI. It has actually had dissolved, and we could cycle it stably up to 80 degrees in this case. We didn't try higher at that time. LiBF4 was a very different story. At 60 degrees, it was really dying, and we had to reform a large part of the SEI, and it didn't work to really get the lithium into the graphite. It really wanted to react with the electrolyte at that temperature. And we can explain that by the kind of Lewis acids formed by PF5 and BF3, where the BF3 seem to be much more reactive than the PF5. And looking at room temperature, we got a smooth, nice lithium fluoride, small crystalline layer of lithium fluoride. These lithium fluoride crystals grow at 60 degrees Celsius, but we still had a nice, smooth sort of polymeric layer in between covering this. While for the LiBF4, we could already at room temperature see much more of the lithium fluoride crystals, and they grow really large at 60 degrees Celsius, and it really disrupted this organic layer. We think that is one key to why this is not working. And I think today, in the research field today, we do discuss a lot the role of the lithium fluoride, and that it has a positive effect when it has this nanocrystalline size. Moving up in time, it was really discussed a lot if we could also use PC instead of EC, a polycarbonate instead of ethylene carbonate. And this carbonate could work at much lower temperatures than the EC, because the EC is solid at room temperature, need to be dissolved in some kind of solvent. But it turned out that this PC just exfoliated the graphite a lot, and you couldn't even get the lithium to go into the graphite and form these stages you typically have. And interestingly enough, this is still today, 15 years later, a big research field where people try to put in different kinds of additives to stabilize the pieces so we can use it and therefore increase the properties at lower temperatures for the battery. At that time, 2004, we thought that this behavior gave you a thick layer, thick SEI on top of the electrode. This is very nice SEM micrograph from Peter Novak's group in PSI showing this exfoliation. But it turned out that this was really gas formation, and that you got the very thin layer on the graphite, not at all the SEI layer you needed. So it was really this exfoliation sort of story, which was the important thing. So what we then use a lot today is HAXPES method. We started to use it early. HAXPES means Hartz X-rays. It's sort of an international term. I think in US, you always want your own expression. So you call it tender XPS. You call pouch cells. We used to call it coffee bag cells. You discovered them a little bit later than we did. But never mind. And the thing is that you can, with these techniques, go to higher photon energies, 2, 3, 2, 6, 8, even to 12 keVs, and really have photon energies making you go deeper and deeper into the bulk of materials. So you can actually, by using different photon energy, probe the outermost surface, with low photon energies, and then go deeper so you can even come to the buried interface of, for instance, a graphite electrode with an SEI. We use a number of different synchrotrons in Europe. I think we can soon add also the one in Hamburg here on the list. And here's just one example of a lithiated graphite. Where you have the SEI, you can't see the lithiated graphite signal. Here you can only see the SEI components. And if you then go to higher and higher photon energies, you can actually see more and more of it. And by doing this, we can learn a lot on what's going on in this battery. I should also say, yes, of course, you can use argon etching and different etching techniques to also sort of move away the layers and go deeper and deeper into it. But it's always risky to do that. It's actually more risky. We have done the comparison, and you get a lot of side reactions, overestimating the amounts of lithium fluoride and lithium carbonate in your results. I usually say that, based on my experience, that if you have results showing a lot of lithium fluoride, a lot of lithium carbonate, you have probably had some problems in your experiments of some kind. So it is actually extremely important also how you handle your electrode. And I've forced my students to do a lot of what you can call engineering studies. Do we need to wash the electrode to say something when you use photoelectron spectroscopy techniques? Or should you not wash your electrode? What does that mean? And my poor students, they have to do both, because we can save something if we wash it, but we also want to see what we wash away. And of course, does it matter if you expose your electrode to air? Will that influence the SEI? And we can say that the SEI is very sensitive, and by checking this kind of protocol where you check washing versus non-washing, vacuum versus air, we have learned that even a short exposure to air will influence the SEI quite dramatically. So all samples exposed to air in this case, it was 4 minutes, like moving the sample from a glove box into the spectrometer, which we are not doing today. We have always transfer chambers. And you get lower amounts of carbon active material, thicker surface layers form, a lot more of oxygen also, and that increased. And if you have lithiated graphite, it actually delithiated during this short time, and you could find then that you had extra lithium oxygen, lithium hydroxide layers on top of the graphite surface. So what do we discuss today? Well, we continue to discuss the composition of the electrodes and the depth profiling, what compounds we see. But we need to discuss the formation of the SEI much more, and of course also the interface on the cathode. But we need to do with full cell concepts and new methods. So in this case, we cycle the graphite versus the lithium iron phosphate. And just to make a long story short, you have the much thicker SEI. You have the inorganic species close to the graphite surface. You have lithium fluoride all through the layer. You have more of the organic type materials here. In this case, depending on the binder you have, you can even have it like almost like a jelly type of electrolyte all the way also in this. The lithium fluoride is very different. It's this much thinner, as I indicated before, and the layer is more like the composition we have in the outermost SEI here on the graphite. And in fact, we can also find a little bit of iron on the graphite surface by dissolution from the lithium iron phosphate. And this is also well known, and it's related also to to interface reactions here, where you have LiPF6 giving you some HF, and therefore also some kind of etching of the lithium iron phosphate. In this system, we also actually try to say something about the buried interface, and that you can do by really looking carefully at different cycles and the kind of signals you have for both lithium Hux pairs and carbon Hux pairs, and also you can see just by the composition, general composition from the surface spectra, that you do have quite a dynamic situation where this SEI is changing, if it's intercalated lithium or deintercalated lithium. So if you do your calculations correctly, you can actually find that in a fully normal and well-cycling system, you actually have a piling up of lithium ions here at the interface underneath the SEI and on top of the graphite. And you form, in this case, then a composition of 1-to-1. And this seems to work, but as soon as you start to have more than one lithium here and build up that interface, like you do in fast charging, you start to have a problem. And we looked at what does this mean really to have this buried interface, and we actually saw that you have to really think when you do your calibration of your spectra, that this is actually something that people, and not even us before this, took into account really well. So if you have a non-cycled electrode, you find the SEI components here. You can take this signal as the SEI component, the CH peak, and you have your carbon-carbon bond. And you form the SEI, and you see that it's shrinking because you have the SEI components building up, and the signal below that SEI is getting smaller and smaller, but you also see a shift. And this shift, we were looking at that shift a little bit extra. And we explain this shift as being important, where you have more of non-conducting species in the SEI. And this is, so you have a certain binding energy difference when you have the intercalated graphite. And this means that you get a lot of dipole moment at the buried interface. And we, in the previous slide, we explained that as a lot of lithium. And when you deintercalate your lithium, you actually remove a lot of that charge. You have a smaller binding energy difference. And this is something you have to think of, especially when you move, like we are doing now, from postmortem studies to more operandi studies. And one more thing when it comes to handling this with the SEI has to do with the gassing. I've already indicated that you can have gas, especially if you have exfoliation. And here's a study we did, a model study, not using graphite, but as a gold substrate, and but with the typical electrolytes that you have in the battery. And we did operandi surface enhanced Raman spectroscopy, online electrochemical mass spectrometry, and electrochemical quartz crystal microbalance. It's my co-worker Erik Berg who's working on this. And if you look at these graphs where we go from the reduction, which means inserting lithium more into the gold, not really alloying the lithium with gold, because that takes place at 0.3 volts. We didn't put that far down. But you can see here that you do form a lot of gases, hydrogen and carbon dioxide, some ethylene as well. And you can see that you have mass changes in this, indicated by EQCl. And we see that the electrolyte impurities you have, like HF and water, are reduced early, and they contribute in a multi-step electrochemical process to an inorganic SEI layer rich in lithium fluoride and lithium carbonate. And if you remember what I said earlier, that lithium carbonate is not really there, I would say in this case, we take that as a sort of name for all the kind of carbonaceous species you have here in this formation. What this was for me as a photoelectron spectroscopy person, it was good to see that you have gases, yes, these will be pumped off in an ultra-high vacuum system, but it seems to not matter so much because it has sort of left also the SEI as it is. So it means that the experiments we are doing in ultra-high vacuum are not that dangerous when it comes to composition. So with this in mind, we continue to study a lot of full cell studies, going to systems where we really want to go in the future, in the near future, next generation batteries, nickel, manganese, cobalt, 811, silicon graphite electrodes, looking at different additives. In this, there's many additive studies at the moment. They are flame retardants, etc. They are additives that are film formers, and in this case, we're taking an anion receptor. And this anion receptor is to take care of the LiPF6 anion and prevent the hydrolysis of that and the formation of HF. You can call it then an HF scavenger, this 3-methyl phosphate additive. And it's breaking these oxygen silicon bonds, which is slowing down an impedance increase even in the battery as a function of the hydrogen fluoride formation. If we can prevent that, we also prevent an impedance increase. And this has also not only protected the cathode, but also as an effective additive to improve the surface stability of the graphite anode. So you can see that only a small percentage of the scavenger, this anion receptor, makes a big difference cycling-wise. You have the baseline, and here you have the same, but with TMSI, you see it's quite improvement. And it's also nice recapability test. By operando XRD, we can also see that it actually influences the cathode. And without the additive, you have not, you have a problematic two-phase reaction taking place with the lithium carbonate layer often found on the surface, which can be crystalline of this NMC electrode. But without the additive, with the additive, you seem to have a solid solution reaction between the additive and this carbonate, which actually is very positive for the function of the battery. And if you look at the graphite silicon electrode, you can also see that the additive leads to clear improvement, and mainly the CF compound formation is prevented. Is this peak here? You can see here at the baseline, and you see it's not here after 53 cycles when you have the additive. So you have a lower amount of HF. It's actually not only good for the cathode, it's also good for the anode. So what you can say is that this additive actually prevents some kind of crosstalk because it's removing this lithium carbonate from the positive electrode, and it also scavenges the LiPF6, which is good for the anode. So it has several good properties in this case. I was given this figure from Peter Novak's PSI. I think it summarizes really well the difficulty we have on the surface with gas formation, with rearrangement of the electrode structure, which can lead to a degradation, and also surface layers, organic, inorganic species that can form but also be destroyed And we have particle cracking when we are cycling. That also leads to fresh surfaces reacting with the electrolyte. So with all these components in mind, we still see then the remaining challenges for graphite, for instance. Fast charging, the risk of lithium plating, influenced by temperature, particle size, morphology, particle orientation, electrode engineering. We still don't really control it in a comprehensive way. It's interesting, though there are so many studies on it. We have the first cycle capacity loss. This is an expensive thing for industry. They are doing a lot of pre-formation cycles before they let a battery come into an application. Can we actually reduce that time and formation cycles by additives, coatings, binders, and also by the electrolyte compositions? Then we would win actually with lower cost batteries. Aging properties, use, how we use a battery, how we drive a car matters also for the battery if it's an electric vehicle. And recycling. And then a lot of new materials and new batteries are coming up as ideas for next generation batteries. This is especially now in Europe, such a hot topic. So we can see potassium batteries, calcium battery, magnesium, solid state, you name it, dual graphite batteries, what you name, what you want. And I just wanted to show you that with the same kind of photoelectron spectroscopy techniques looking at potassium, we can actually say something also using HAXPES. This is the carbon S peak, moving along the insertion of potassium and the extraction of potassium and say something. And you can already, by the cycling curves, say, oh, we have a large capacity loss during the first cycle. Yes, we have. And why is this? Well, we have the graphite, we insert the potassium, you get enormous SCI layer. But even worse is that it's actually shrinking a lot again when you are removing the potassium, which means that when you take your second cycle, you actually have to form this again. It's taking a lot of potassium again for the second cycle. And with the photon, this kind of techniques where you do this depth profiling, we do actually can say that a lot about also how the compositions and depth profile of this works. And in this case, it's so dramatic, so we can have a very simple conclusion. Newer electrolytes are needed. They are really important. And of course, we can see all this. We have tools for that, but how can we reach to the next stage? And that's, of course, try to use some operando ambient pressure studies. And we are really working on that for solid liquid interfaces in Uppsala. You can find many papers coming out now in this field on solid, but also solid and non-volatile electrolytes. And that's good. But if you want to go to the typical electrolytes, you have the commercial batteries today. That is a challenge. We are working on new instrumentations and go to millibar pressures. We're working on new sample chambers where you have your sample, you have an analyzer, and you have like a little bubble around it where you have your millibar pressure, and then you have a system where you actually increase the vacuum for the electron that you are to probe. So you have several stages of pumping to really reach that outside the compartment where you really take out the electron. We are working in a specific beamline at Max IV laboratory that's built up by Uppsala University called HIPPY. And you can see here is the analyzer, here's our sample. And there are many different ways of trying to do this, having like a little beaker where you can move up and down your sample, have your analyzer. And this is an Uppsala variation where you have your electrolyte in a little compartment here, and you can rotate your electrode. And it's a lot of work behind this. It's a lot of model system looking at, can we get the resolution? What will happen with time? Can we say something about the pressure you need to have around your sample? If we are studying a PCl molecule on a surface, can we then have nitrogen-based pressure in the chamber? No, it seems to have PC gas around the liquid is actually better. How about the radiation damage? How is it with that, etc. So we have some studies on this you can have a look at. And we have also looked at a droplet where you have the lithium metal and look at the droplet out here and the droplet in here using this kind of Huxley's idea. And you can say then something about the composition of the layer on the outside of the droplet and close to the lithium metal. And that's quite interesting because you do see a difference. What does that mean when you have it translated into a real electrode? That's what we are trying to do now here by working on different methods with droplets and then applying electrochemistry on it. And we can say something that we can see now. Liquid electrolyte can be maintained during the measurements. We have to change spots to reduce influence of radiation damage. We need to be characterize the electrolyte surface for correct interpretation of results. We have salts accumulated at the surface. And there are lithium ion accumulation also on the surface. And we can now perform battery operando measurements, but we are doing a lot of method development at the moment, and we are right in the process to publish a paper on how you actually calibrate your peaks you find, because it's suddenly we are not at all at the same kind of thinking as we were with the postmortem studies. I hope that's something I can talk about another time. And in this big European newly started pan-European project, Battery 2030 Plus, we will try to accelerate the understanding of with the help of high-throughput experiments in combination with modeling. By using artificial intelligence, machine learning, the whole multi-scale modeling toolbox, together with work with Soleil, ESRF, ILL, and try to find a way to not work linearly, but more integrated between modeling and experiment to really make a new effort to learn more about this. And when it comes to the examples I've shown here, I concentrate on carbon and graphite materials. I could use many other materials, of course, but they will continue to play such an important role for the sustained batteries of the future, almost irrespective of what kind of battery it will be. And that's because of they have many shapes and forms. And I have talked so much about the SCI. I should have talked more about the CEI, of course, but there are many other interfaces also that we have to think about that play a role for a battery and for all kinds of batteries, also the batteries of the future. And we also have to think along the whole value chain of battery and what that means to the interfaces. Always the chemistry that decides what's happening in the battery, irrespective of the system level. And I'd like to thank all of my co-workers. There are so many I would like to mention. These are just some. So there are so many important at many places, and funding agencies, and even more funding agencies. And I thank you so much for listening to me. Thank you.